Now that we've looked at the example overview, we'll visualize the hook methods. This, again, should not be a big surprise. And that's by design, right? The whole point of this stuff is that when you write code with streams and parallel streams, it all typically looks pretty much the same. The main difference, of course, being you get a big speed up in performance relative to the number of cores that you have at your disposal. So processStream searches the list of input strings in parallel. You give it a list of input strings. The parallelStreams method is called. Each of those input strings, of course, is going to be a different work of Shakespeare. We call parallelStream, and now this is going to feed into the parallel processing on these chunks. What happens under the hood is a split iterator is used to split the input up into different chunks, and essentially it ends up with one chunk for each element for each input string. It's kind of the way it works because it's an array list. And if you recall from your array split iterator, it chunks things up into elements of size 1. So we'll have things chunked up quite nicely. And then these input strings are processed in parallel in separate threads and cores. We're going to go ahead and take the stream of input strings, and then the map intermediate operation is going to be used to call them. And keep in mind what's going to happen here is this map operation we'll call processInput in parallel in different threads running in the thread pool. So we're going to be taking each work of Shakespeare and processing it in different threads of control. And I'll show you visually what that looks like shortly, because it's really cool. The consequence of calling processInput, as you may recall, is get back a list of search results. And we take that list of search results, and we have a stream of lists of search results. And then we're going to go ahead and collect those things together. And that, of course, will trigger an intermediate operation processing for the map call here. And that, of course, will all run on those different worker threads and cores that are part of the fork join pool. And recall that collect will collect things back in counter order because it was a list. And so we'll end up with a list of search results based on the encounter order. So all these things will come back here. Everything will be collected up properly. And here then is the processInput method, which is going to take a given input string and the phrases. So it again will convert the search phrases into a parallel stream. So these things will also be processed in parallel. So the different chunks will be thrown into the same common fork join pool. And I'll visualize that a little bit later. But the way to think about this is that each input string will run in its own chunk in the fork join pool. And each phrase will be searched for in a chunk in the fork join pool. So we're kind of really mixing this stuff up in a fairly reasonably fine-grained level, having both strings and phrases matched in parallel with the fork join pool. So these things will be running in parallel. It's going to go ahead and search that given input string for each phrase. All those things will take place in parallel, so it'll search for the phrases on a given input string in parallel. And we'll end up with a bunch of search results. We will filter out search results that are empty, so we get rid of them. So we'll end up with only non-empty search results. So filter will reduce the number of results. And we collect it up into a list. And then that will trigger the intermediate operations to run. And we'll end up with a list of results that are based, again, on encounter order. That's basically what it's going to look like here. And keep in mind, I'll talk about this a lot later, but the particular kind of collector that's created by toList is something that's called a non-concurrent collector. And we'll talk about concurrent collectors later, and we'll differentiate concurrent collectors from non-concurrent collectors. Both, this may seem a little odd, so I'll cover it later as well. Both concurrent and non-concurrent collectors can work just fine in a parallel stream. You might think, well, how can you use a non-concurrent collector in a parallel stream? And it turns out that the streams framework makes sure that when it merges the results of sublists, it only ever does it in one thread of control to avoid any race conditions that would occur if you were doing the merging in multiple threads. So non-concurrent collectors are handled properly even in parallel streams. And we'll compare and contrast that probably next week. Now, keep in mind, of course, as I've talked about many times, that it may appear at first glance as if the processing is done level by level, but in fact, it actually works by pulling the data through the stream one element from the source at a time. And when you have parallel streams, you'll end up with different threads in the pool, pulling the elements from the data source in different ways. And that's what the splitterators are all about. They split the input up into chunks. Those are handed off to the threads in the fork join pool, and then they pull the data through when the terminal operations are reached. And the reason for doing that is to make sure that, first of all, you can have short circuit operations handled correctly. You can also do something called integrated layer processing, which is a optimization that makes things run faster by managing cache memory better. So that was a quick overview of visualizing the behavior of this program. And I think you can kind of get a sense for how it visually looks a little different from what we had done with the sequential version.